In the last several lectures, we've talked about two methods, right? The addition rule and the multiplication rule, for answering some basic questions about the number of ways that objects can be ordered. Now, these are both great tools, right? But they're not very precise, both in terms of what questions they can answer or how they go about answering them. Now, the processes themselves are well defined, but we need to be able to describe them more precisely if we're going to be able to extend them to answer other types of questions. So in this series of lectures, we're going to start by refining and better defining those methods. Then we're going to look at ways that they can be extended. And we're going to use this question here about seating arrangements, which can be easily answered using the multiplication rule to drive this lecture's discussions. First, let's talk about terminology. All of the examples we've been talking about so far have been examples of what we call permutations. Right? Permutations are arrangements of objects where the order matters. And you can see that in my example question here. Seating Alice in the first seat is different both to her and to the people watching than seating her in the second seat. So the first part of the question, where we're seating everyone, would be a 10 permutation. And the second one, where we're doing a partial seating, would be a 6 permutation. Now, these last two symbols, that would be P10 comma 10 or 10P10 for the first scenario, or P10 comma 6 or 10P6 for the second one. These refer specifically to the number of possible permutations we can come up with by choosing R elements out of a set of N elements. So R permutations refer to a single specific arrangement of R elements, where the two P notations refer to the total number of possible R permutations. So before I go any further, there is one more notation that you need to be familiar with. And if you already know what a factorial is, then you can skip this slide, go on to the next one, and you'll be just fine. Right? What a factorial does is it's a shorthand way of writing a specific kind of multiplication. Right? In all of the questions that we've been answering so far, there comes a point where you end up multiplying a series of integers together. Right? For example, if we look at this seating 10 people in a row of 10, or where we're seating everybody, then you know how we did this using the multiplication rule. We do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seats, and we have 10 people we can put here, then 9, 8, and so on, down to 3, 2, and 1. And what do? We multiply all these numbers together. So the result here would be 10 times 9 times 8 times 7 times 6. That gets really old really fast, especially when the number of objects that we're dealing with starts to get big. So we have this factorial notation, right, which is a way of shortcutting this. So instead of 10 times 9 and so on, I would just write this as 10 factorial. And that's what the exclamation mark means. Right, so when you see this, 10 factorial means take every integer from 10 down to 1 and multiply them together. Right? And just throwing a couple more quick examples up here. 3 factorial would be 3 times 2 times 1, that's 6. 5 factorial would be 5 times 4 times 3 times 2 times 1, that's 120, and so on. Right? This comes up a lot in the kinds of counting questions that we're going to be talking about, this idea of multiplying a sequence of consecutive integers together. So it's going to be helpful to have a notation to shortcut that. And there is one other special value here I need to throw out to you. And I know this is a little weird, all right, but 0 factorial we're going to define to be equal to 1. Why? Well, because it's going to make our life a lot easier. There are some kind of technical reasons why we should do that. But for now, let's just say it's going to make things easier for us as we go along. And all of the questions that we try to answer are going to work out just fine, exactly the way they should be if we use that value. All right, so let's look at these two examples here. What I'm really building toward is coming up with some kind of formula. I'm thinking probably using that vectorial notation to describe the number of possible permutations of R objects taken from a set of N objects. And before I just jump in and start thinking about that at that kind of level of abstraction, I want to look at these two specific examples. Right? And then we'll compare the results that we get from each one and see if we can kind of use that to reason our way into the formula for the general case. So putting 10 people in a row of 10, I'm actually going to write this out. That came out to 10 times 9 times 8 times 7 times 6 times 5 times 4, 3, 2, and 1, which, as I pointed out on the last slide, right, this is 10 factorial. All right, so how about if we're only seating 6 people? All right, well, to do that, we've got 6 seats now, right? So I'm going to do 1, 2, I'm going to do this 6 times. 8, 7, 6, 5. That's 6 seats. Right, now, this doesn't come out so nice. We don't really have a factorial notation for describing a product that cuts off before it gets to 1. Right, but here's what I want you to notice about this. Right, what is the difference between these two? Well, the difference between them is this part right here. Right, and this part, 4 times 3 times 2 times 1, this is 4 factorial. All right, so if I take the 10 factorial that I got from the case where I was seating everybody, and I divide this by 4 factorial, that's going to cancel out that 4 times 3 times 2 times 1, and all that's going to be left is this. And that's my answer to this, like I called it earlier, the partial seating case. All right, well, let's think for a minute about that 4. Where did that 4 come from? Well, I have 10 people, right? I have 10 people, and I seated 6 of them. So that 4, in a sense, that 4 is the number of people who didn't get seated, right? So if the whole thing is 10 and this thing is 6, then this part here is 10 minus 6. But you notice those were the two numbers in the original question. Right? So I could rewrite this, and it's going to seem a little odd to do it this way here, but just bear with me. This is 10 factorial over 10 minus 6 factorial. All right, so now let's see if we can generalize this and just kind of drop some numbers in here, variables in here instead, right? So let's say instead of doing 10 people, we have n people to choose from, and instead of seating 6 of them, we're going to seat r of them. All right, well, so what does this look like then? Then there's going to be, this 10 factorial is going to be n factorial. That's the number of permutations where I'm seating all of the people together. And this, let's see, this is going to be R, right? Because we're seating R people. That means that we are not seating N minus R. All right, so let's see how that adjusts my formula down here, right? The numerator is n factorial. The number of ways we could seat everybody. We're going to divide that by n minus r factorial. That's the number. Essentially, that's the number of ways we can choose the people who didn't get seated, right? In kind of a backward sort of way. And that's a very nice generalized formula for this. So what I've got here is our definition again, right? This is the same definition I had on the previous slide. Only now I've added the formula that we've developed, right? And this is the kind of generalized version of the multiplication rule that I was looking for. This is the kind of thing that we can work with in terms of trying to expand it and use this as the starting point for answering wider classes of questions. So I've got our question here again. This is the question that we've been building on this whole lecture. What I want to do is I want to see how we can answer this using our formula, right? So we can really kind of see the formula in action. Right? So if we want to seat 6 people, we have 10 people, we want to seat 6 of them. So that means n is 10. That's always the size of the parent set, of the main set, right? Of the big set that we're taking our selections from. R is going to be 6. That's the number of people that we are actually going to pull out of the larger group. And so what am I looking for? I'm looking for 10p6, which is how I would read that. And according to my formula, this is 10 factorial over 10 minus 6 factorial. That's 10 factorial over 4 factorial. Now, your calculator will easily do this. Right? Today's calculators will actually do very large factorials. Obviously, it only has so much space on the display. It's only going to show you the first 10 digits or so. But in memory, it is actually holding on to the full number. So if you went to, if you have a scientific calculator and you did 10 factorial divided by 4 factorial, it would give you the right result, right? But let's work this out ourselves, just kind of see what's happening. This is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 over 4 factorial. 4 times 3 times 2 times 1. And yeah, now we get a lot of cancellation, right? All of this stuff cancels, and we're left with 10 times 9 times 8 times 7 times 6 times. So you see why we really like having that factorial notation? And my calculator tells me that this is 151,200. Okay, so that's 10 people. That's 6 people taken from a group of 10. How about the other one? How about if we're going to choose the entire group of 10? So now n and r are the same. So this is the kind of thing mathematicians and computer scientists really like to focus on. It's called an edge case. When we get to this case where we have 10 people and we're choosing all of them, okay, it's at the edges where things can sometimes get a little weird. So this is the kind of situation you really want to check and make sure your process is doing what you want it to. So again, if we go to the formula, 10p10 is 10 factorial over 10 minus 10 factorial. You see how this is about to get weird? This is 10 factorial over 0 factorial, and this is why we really want to define 0 factorial to be 1. Right? Because if that denominator is 1, then this is just 10 factorial, and yes, that is exactly the result that we expected going back to the multiplication rule. All right, now let's look at another edge case. This isn't on my example up there, right? But let's look at another edge case just to kind of see what happens. Suppose I want to choose nobody, right? How many ways are there to choose nobody from this list, right? So in other words, I want to do n equals 10, r equals 0. Another edge case, kind of a bizarre edge case, okay? But still, the kind of thing we want our formula to be able to handle, right? So let's see what our formula says. 10p0 is 10 factorial over 10 minus 0 factorial, which is 10 factorial over 10 factorial, which is 1. Yeah, I'm okay with that. You might have to kind of turn it around in your head a few times to see it. But yeah, how many ways are there to choose nobody? Well, it is a choice, right? You do have to make a choice, and there's only one way to do it, right? You have to put nobody in either of those 10 seats. So yeah, okay. It does kind of make sense that we're coming up with 1 here. Okay, so we've accomplished what I wanted to accomplish here. We now have a very specific idea of the kinds of questions we can answer, right? Questions that involve arranging people, arranging objects in a series where the order that I pick them makes a difference. And we have a formula. It's really good to have formulas because formulas are the kinds of things that we can manipulate to come up with new formulas, to come up with new methods, ways of answering different kinds of questions. And that's what we're going to do in the next lecture. We're going to kind of answer what to a mathematician anyway is sort of the obvious next question. Well, if we can count the number of ways that we can arrange these people in an ordered list, can we also count the number of ways that we can put them in an unordered list? That's what we're going to talk about in the next lecture.